The last special diode we're going to talk about is the Varactor diode. This is a PN junction diode basically that's just been designed to take advantage of the fact that there's a relationship between capacitance of the depletion region and the width of the depletion region. So resonance is something that happens whenever there are waves or vibrations that kind of get in sync with each other. So if you have, say, a musical instrument and it's designed so that there are strings on it perhaps that vibrate, and then perhaps the wood that it's made out of also vibrates at certain frequencies. That's just reaching a point of resonance. Electrical resonance happens in circuits when you have a capacitor and an inductor, and they actually work together to transfer energy from one to the other. So the magnetic field of the inductor collapses, and that produces current, and that charges a capacitor, and then the capacitor discharges, which produces a current that makes a magnetic field in the inductor, and so forth. So this is something that's desired because frequently we need circuits in which the capacitors and inductors are at resonance. The way this works is the impedance, or how much the capacitor inductor impedes current from flowing through the circuit. The impedance has to be exactly the same. This is a frequency-dependent kind of association, but it is very difficult to find a capacitor and an inductor that have the exact correct values at the exact right frequency. Usually you can get one of them, but then the other needs to be adjustable. So oftentimes we use adjustable devices. So you see how the energy goes back and forth between the capacitor and the inductor, and it happens at a particular frequency. So this is just basically mathematically telling you what I just told you in the previous slide. So if you can find an adjustable component, then you can find this frequency easier. You can produce an oscillator out of this kind of application. So that's basically a circuit that will self-generate a sinusoid at a certain frequency. So that's something that is very precise. It needs very precise components. And you can find variable inductors, but inductors are big and they're lossy. So we're going to talk about a variable capacitor. And this is actually a semiconductor device. So it's known as the Varactor diode. So capacitance occurs when you have a separation of positive and negative charges. Capacitance depends on how far apart the charges are, what's between them, so whether it's air or some kind of material, and the cross-sectional area of the charges, the plates that are holding the charges. So the dielectric, what's between the charges, has a permittivity that's just part of its nature. And then we have the cross-sectional area, it's directly associated, and then you'll notice the distance between the plates is inversely proportional to the capacitance. So as the distance increases, the capacitance would go down. In the depletion region in a diode, that is a separation of positive and negative charges. So all PN junctions have some kind of capacitance associated with them. If you apply a voltage, you can change the width of the depletion region, especially in the reverse direction. So as you apply more voltage, the depletion region will just continue to get wider and wider. So a Varactor diode takes advantage of the relationship between the reverse voltage and the width of the depletion region. So it's designed such that the anode, of course, and the cathode are exactly the same as a regular diode, and the plus and minus are given. So if you wanted to forward bias, you would give forward bias in that direction, but we don't. We generally use these in a reverse biased direction. So the way these are made is they are constructed such that we use them in a reverse, and as the voltage increases, the increasing width between the two charges results in a decreasing capacitance. So it's not a linear relationship, but it is a relationship. It ends up actually looking like this, where the capacitance is the highest when you don't have reverse voltage, and then it decreases as you increase the voltage, and eventually it reaches a kind of a flattening point where it doesn't decrease anymore. So we can look at one. We actually have a Varactor diodes, and you can see this circuit in which there is a variable DC voltage source marked, and this is the same circuit, just one from the front and one from the side. And then there are two Varactor diodes. This diode, which corresponds to this one, is the one we're actually measuring the capacitance of. And then the other one is being used as kind of an isolation mechanism. And then this resistor here is just limiting the current that's coming in. So we have a voltage right here, and then a current going this way. And then this right here is reverse biased. And we're measuring the capacitance. And what you'll notice is you can see the voltage that's being applied here. And you can see it changing. And then this is the capacitance. And you'll notice that as we run it, the voltage starts out small, and the voltage is increasing, and then the capacitance is going down as the voltage increases. And when you finally get to a point where the voltage gets to its maximal, then the capacitance is the minimum value we can get, which ends up being around 36 or so picofarads, I believe, something around there. And then if we end up taking the voltage back down, we will end up increasing the capacitance again. So that's how a Varactor diode works. And the only thing that you would want to take out of this is the conceptual idea of what a Varactor diode does.